Welcome to Chapter 3, Elements, Atoms, Ions, and Isotopes. A little review. An element is a pure substance, and it can't be decomposed by ordinary chemical means. And we know that an atom is the smallest unit of an element that still has its properties. If we're looking at the history of chemistry, we started off with 4 elements in alchemy, and earth, fire, water, and air. And we've come a long way since then. Around 400 BCE, Democritus and his mentor came up with the idea of atoms. It's the first documented idea of matter. And Democritus suggested that if you keep dividing it, you end up with smaller and smaller particles that cannot be divided. And he called them atomos, or atoms. And then much later, around the 1800s, John Dalton proposed atomic theory. And it totally changed chemistry. And instead of wizardry, alchemy, now we know it's chemistry. Dalton's theory had 4 proposals. He said that atoms are indivisible, indestructible particles, and they have their identity that keeps the same throughout chemical and physical changes. The second one is the atoms of the same element have the same mass and the same properties. If it's a different element, it has a different mass and different properties. His third tenet was that atoms of different elements can unite in different ratios to produce more than one compound. So we can look at this if we say we have water, H2O. Okay, that's something we can drink. But H2O2, same elements, different ratios, is hydrogen peroxide. And if you drink hydrogen peroxide, you will become very ill. Lastly, in a chemical reaction, the atoms are rearranged. They're not created or destroyed or changed into atoms of any other element. So this is where the law of conservation of mass started. If we look at these proposals, some things are inaccurate because of our new knowledge. For example, elements are indestructible and you can't divide them. Now we know we have subatomic particles, protons, neutrons, and electrons. And also we know that nuclear chemistry can change the identity. That's not ordinary chemistry, but it's still chemistry. Another piece of new knowledge is that isotopes of the same element have different masses, and we'll be learning more about them later. If we look at proposal number 4, this is true in ordinary chemistry, but once again, nuclear chemistry brings around some changes. Although I would say Dalton did pretty well in the 1800s to come up with things that are primarily true even today. Then we have Thomson's cathode ray, and this was the first discovery of negative charges, what we now know as electrons. And so a cathode ray is negatively charged particles in a tube that has been evacuated or that has a vacuum created. If I put a positive side of the magnet, the rays were attracted, and so the rays must have been negative. He also said that there must be positive charges in this atom because the overall net charge of an atom is neutral. Thomson had this cathode ray, so the particles were generated by this anode, the negative plate, and drawn through the cathode, and then they would hit this fluorescent screen. When he put magnets or charged plates to them, the rays were drawn to the positive side, and so he knew that the rays must consist of negative particles. He didn't know the numeric charge, nor did he know the mass, but he could calculate this ratio. And as a result of his work, we came up with the plum pudding model. Plum pudding model has this evenly positively charged sphere, so the charge is spread throughout, and then the electrons are studded within it. Plum pudding is an English dessert, sort of like raisin bread. Then in 1909, Rutherford did a gold foil experiment. He came up with particles, again, and he bombarded them towards this gold foil, very thin, almost as thin as gold leaf. And the particles, if they hit this outer ring, would fluoresce. Let's take a look at what Rutherford expected. We have our plum pudding model, so the positive with the negative light blue electrons, and if you put the particles, he expected them to pass straight through. But what actually happened is, if you watch the particles, you can see they are deflected. Some go to the side, some go almost perpendicular, some are even knocked straight back. And so Rutherford hypothesized that there was this nucleus inside, this positive charge that was hitting the particles and bouncing them off. And here's an example of what he expected and what actually happened. Rutherford came up with the nuclear theory, and most of the mass and all of its positive charge of the atom are in the small core we call the nucleus. Most of the volume is empty space, and we have these extremely small negatively charged electrons spread throughout. The number of the negatively charged particles, the electrons, is equal to the number of positively charged particles, the protons, so overall the atom is electrically neutral. To sum up, we can say protons have a positive electrical charge and their mass is very small, 1 point, etc., all the way negative 24. That means there are 23 zeros before the 1. Instead of writing those small numbers, we have come up with a unit, atomic mass unit, abbreviated AMU, and we say that the proton has approximately 1 AMU. Electrons have a negative charge. They are so small, they are 1/2000, 0.0005 AMU. So we round them to 0. The neutrons do not have an electrical charge, but their mass is very similar to the protons. You do not need to know this extremely small number, but you do need to know this chart. And if we're thinking about size, the size comparison, the proton was the size of this baseball. The electron would be the size of a rice grain in comparison. So we know that opposite charges attract and similar charges repel. Matter is typically charge neutral, meaning it doesn't have a charge because equal numbers of positive and negative charges, and those cancel. An example of this is an electrical storm. So we have the charge balance being disturbed. We have a negative charge buildup, and then there's a quick rebalancing. The energy goes from the negative side to the positive charge buildup, and we see lightning. Dalton said that particles were indivisible, but we know that they are made up of smaller particles. And the first division, or the next smallest particles, are quarks, and they make up protons and neutrons. There are 6 types, and it takes 3 quarks to make a proton or a neutron. The names are up, down, strange charm, top, bottom. And it takes 3 to make a proton and 3 to make a neutron. You're not responsible for those. All you need to know is the definition of quarks and that there are 6 types. So I said that opposites are attracted, but the same charges repel. Well, in our nucleus, we have protons. They have the same charge, they're repelling, and neutrons have no charge at all. How does the nucleus stay together? There are nuclear forces, and when particles are extremely close to one another, they are attracted. This is similar to gravity. So we have attractions then between the neutrons and the protons, between the protons and protons, and also between the neutrons and neutrons. And so that holds the atom together. When we're looking at chemical compounds, a little review. Compounds are more than one element that are chemically combined, and you can decompose those chemically to those particular atoms. Sodium chloride is an example. A molecule is just 2 or more atoms. So while sodium chloride is also a molecule, hydrogen is a molecule because it is 2 atoms that are bonded. It does not qualify as a compound because it is only one type. And then we want to look at formulas, and formulas give us our composition of these molecules and compounds. And here's one of my favorites, caffeine. Examining our chemical formula, we have subscripts, and subscripts are to the right of the atom, so they tell us that of the number before. So we have 5 carbon and 12 hydrogen. In our sodium chloride, we have 1 sodium and 1 chloride. We do not write ones in formulas. We can't change these subscripts because if we change them, we're going to change the compound. Another number we need to look at is the coefficient, and this is a very similar idea as to math. It's the number in front of, and so it tells us we have 6 of these molecules. So if we want to sum up the carbon atoms, We have 5 in each molecule, and we have 6, so we have a total in this sample of 30 carbon atoms. We have 12 hydrogen in each molecule. Because there are 6 molecules, we have a total of 72 hydrogens. Some formulas have brackets. So for example, we have sodium, oxygen, and hydrogen. We have a hydroxide. So that's 1 sodium, 1 oxygen, and 1 hydrogen. However, we also have this magnesium hydroxide that has a parenthesis, and the parentheses followed by the 2 tells us we have 2 of everything in the parentheses. So we have 1 magnesium, we have 2 oxygens, and 2 hydrogens. Pause the video and try these practice problems. We have 1 sodium and 1 chloride. 1 molecule has 3 potassium, but we have 2 molecules, so we have 6 potassiums and 2 phosphides. In our next molecule, we have 1 sodium, 1 nitrogen, and 3 oxygen. When we look at strontium nitrate, a parenthesis with a subscript, we have 1 strontium. Each nitrate has 1 nitrogen and 3 oxygen. Because we have 2 of them, we have 2 nitrogens and 6 oxygens. You can think of distributing that too. Here we have both the coefficient and a parenthesis with the subscript. If we look at 1 molecule, we have 2 nitrogens, 1 lead, and 6 oxygens. But we have 5 of these molecules. So we have 5 lead atoms, we have 10 nitrogen, and we have 30 oxygens. Chemistry has a language of its own, and we've already learned some of the element symbols. It's important that the first letter is capitalized, but if there's a second letter, it is not. There is a big difference between cobalt or carbon monoxide, so be sure to make those clear. Lots of chemical symbols are based on English, but we do have some that are based on Latin. Potassium, for example, is K, and sodium is from the Latin. We also have some others here. We have lead, mercury, iron, silver, and the lead is an interesting one. Water pipes used to be made out of lead, and so plumbers were those who worked on the lead plumbum. When we write an element's name or a compound's name, we do not capitalize it. The only exception is, of course, if it's at the beginning of a sentence. We also have elements names that reflect their properties. Argon is inactive, and argos in Greek means inactive. Bromine also comes from a Greek word, bromos, meaning stench, and bromine vapor has a very strong, irritating odor. We have elements named after countries, and then also after scientists. One of my favorite is curium, named after Marie Curie, who helped discover radioactivity and also discovered 2 new elements. She won 2 Nobel Prizes for her work, which was very unusual because she was a woman in a time that women scientists were not encouraged nor acknowledged. And her husband was nominated first and refused the Nobel Prize unless she also was nominated. Glenn Seaborg is the only person for whom an element was named while he was still living. That is because he discovered 8 new elements. The element named for him is Sb Seaborgium.